Hi, I'm Adam. Welcome back to Godot Game Lab. In this episode, we'll implement the basics and the foundations of our UnitAI system using a finite state machine solution. If I go into a battle here, you'll see if I press E that starts moving Björn on the game board, but he immediately goes into a stuck state because both of the neighboring tiles are occupied and diagonal movement is not permitted in the game. But if I press Q, this Robin will start moving, essentially making moving available to the Björn unit as well, so they both go to the chase state where they pick a random enemy target, and when they arrive at their target, they go into this auto-attacking state where they stay forever because these states are just placeholders for now. If you go to the output folder, you'll see that we have one-time output window messages that both of these units should perform attacks. But this is not yet implemented in the game. So let's see how we can implement this with a slight twist on the finite state machine from the Slate Aspire course. So for the architecture part, this episode will be pretty simple. We want to introduce two new components to the battle unit scene. The first one will be a finite state machine, which will be quite different from the one we did in the Slate Aspire course, again just to show you variations for the same thing. We'll use this finite state machine for the AI behavior of the unit, but that will be a separate component on its own called UnitAI. And you might ask, why do we need a separate component for the UnitAI and the finite state machine if the UnitAI depends on having a finite state machine? Well, the answer is reusability, right? So for components, we want to make sure that we can plug and play them anywhere we want in the project. And if later down the line, we want to use a finite state machine for items or something like that, we can just drag and drop the already tested and working finite state machine solution, right? In this specific case, this finite state machine will use a base class called state, which will be the mother of all states in our project. But more specifically, in the case of UnitAI, we have to implement 4 different states: chasing other units, being stuck, auto-attacking, and casting the ability the unit has. And just to provide an overview what we have so far, or what we'll have by the end of the episode, you'll see, for the sake of simplicity, the already existing components are not listed on this diagram, but we do have them. So you can see the node structure on the right. The battle unit consists of these components and nodes thus far. So the new ones will be the finite state machine, the UnitAI, and you might have noticed that we have a new label called FSM debug. This will be used for debugging purposes to see and display what state the unit is currently in. So that's it for the architecture part. Let's move on to implementation, shall we? I already hinted that this finite state machine implementation will be quite different from the one we did before. Why is that? Well, for the Slate Aspire course, we used a node-based finite state machine system, which is fine and has its own pros, right? Probably the biggest advantage of using that solution is that when you open up a scene and you take a look at that finite state machine, it's quite self-explanatory what's going on. You can see it in the node structure, and it's also pretty easy to just find the script you're looking for when you want to make a change or when you want to adjust things. Probably a downside of that solution is that using nodes is a bit verbose, and also it can be costly in terms of performance, right? Because nodes have this overhead connecting to the node lifecycle, and a bunch of stuff needs to be implemented for nodes. So there are 2 documentation pages we can refer to when we are looking for an alternative solution. And the one we have here is for RefCounted objects, which inherit from object class, which is the most bare bones you can have in Godot. So we have this description here. I won't go ahead and read the whole thing. What's important is that you don't have to manually manage the memory for these objects, because if you use the most barebone class, the object class, then you need to manually free those objects to avoid creating memory leaks in your game. You can see right here, RefCounteds do not need to be freed manually with object.free. Okay, so why would we use this, or what's the difference compared to nodes? We have another documentation page called When and How to Avoid Using Nodes for Everything, which is a really good read. It has this whole description of what alternatives you have and when you might use that, or what advantages using that specific object provides. So we have object here, we have RefCounted and resource, right? We already know resources quite well. So for RefCounted, it says only a little more complex. They track references to themselves and only deleting loaded memory when no further references exist. So it says that an example would be the file access object. So when you create a new file access object to load the content of a text file, for example, then you would use this RefCounted class. So when the thing you do in that script is not really strictly connected to the life cycle of the nodes, then you can use RefCounted as well. I'll link both of these doc pages in the description of the video. So what is reference counting? Let me give you an example. Let's say that for a birthday party, someone decides to blow up a balloon, right? We would say that since nobody's holding it, the reference to that balloon is 0. However, that's highly unlikely because when we blow up a balloon, we don't usually leave it unattended. We either tie it to something or give it to someone, right? So when we give it to this girl, then the reference counter goes up to 1. And this is what happens when we create a new RefCounted object anywhere in our script. So you see now the balloon is tied to the memory because it's held by this girl. So if another person comes up, this boy, and he starts to hold the balloon as well, we might say that he references that balloon. Now the reference counter goes up by 1, so there are 2 objects referencing that balloon, holding it, right? But if the girl decides to let go, then we decrement the reference counter by 1, saying that there's still a reference in the memory to that balloon object because the boy is still holding it. And the interesting bit is what happens when the boy lets go, right? Both of them decided that they no longer need the balloon, so what happens when the reference counter reaches 0, the balloon flies away, representing that this object can be deleted from the memory because it's no longer needed, right? So that's how reference counting works. Whenever the counter reaches 0, we know that it's safe to delete that object from the memory because there isn't anyone depending on it anymore. So in this project, instead of using nodes to represent states, we'll use this reference counting technique. In Godot, we already have the implementation. We just need to extend from the RefCounted class instead of node. And let me also take the time to shout out Ben, or Heartbeast as you might know him, because we had an interesting talk about state machines a while ago, and he sparked this idea in me to show this RefCounted implementation instead of a node-based one. So thanks again, Ben, for that nice discussion. Okay, so I have the project open here, and the way we want to implement this is that we start from the bottom and go all the way up. So UnitAI will be the last thing we implement, and we start from the bottom, the smallest part of this whole UnitAI and finite state machine part, which will be the state itself. So let's go into our components folder in the file system doc, right click on it, create a new script, and we'll call this state.gd. And instead of inheriting from node, we'll just type RefCounted. Please note the uppercase C, right? Click on create, expand the folder, and double click on state.gd to open it up in the script editor. And we start by providing a custom class name called state. We also need to have one variable reference to the actor that we want to attach the state machine to. Please note that this can be anything because we want it to be as reusable as possible, hence the node type. So we want to make a system where we can attach a state machine and states to any node we want in the whole project. In this case, we will attach it to a battle unit, but we'll make that typecasting to have auto-completion when we actually implement the specific states like the stuck and the AutoAttackState and so on. Here we just say that it's for sure a node. We'll also override the init virtual method, saying that whenever we use state.new to create a new state, we have to pass in an actor node as a parameter to make sure that we set that variable when we create a new state. If we press and hold Control and click on init to open up the documentation page, it's defined inside the object class, which is, if you remember, the most bare bones thing we have. And it says it's called when the object's script is instantiated, oftentimes after the object is initialized in memory. It can be also defined to take in parameters. This method is similar to a constructor in most programming languages. So basically, when we create a new state, we can pass in parameters and execute logic. It's similar to ready, but it happens sooner, because if you think about it, ready is tied to the scene tree, so we cannot use ready here, right? Because remembering, this is not a node. It does not extend from a node. So we don't have access to ready or process or physics process because this is not part of the scene tree. It's just inside the memory, right? So we have this init class to initialize this state, and we need to have an actor, a node passed in, and we can set the actor to the new actor we have. Then we'll define custom functions for handling the physics process and the process ticks inside the game. But please note, and that's really important here, we don't have a leading underscore. This is a public custom function because, again, RefCounted classes cannot have access to any node related logic, right? So if I start typing func and underscore, you'll see we have init and notification, set, toString, a couple built-in virtual methods, but we don't have ready or process or physics process here because, again, we don't derive from node. Then we do the same for the process, and these are empty here because the base state does not have to implement any logic. So this will be just empty methods, and whenever we actually implement a specific state like chasing units or attacking or something like that, then we might have to override this, right? Because those specific states will extend from this state that we are currently implementing. And we have two other custom methods. One will be called enter when we enter this state once, and the other one will be exit, which will be called when we exit a state. And that's the most basic like skeleton we want to have for states. We have this initialization where we set our actor, and we have 4 public methods which can be overwritten by specific states that will be extended from this class. Again, please take a note that process and physics process here does not have leading underlines. Okay, so let's save this script with Ctrl S. And there isn't much we can really test here, so you need to bear with me and implement the next part. So we have to build everything from the ground up and have this system ready to go when we want to test it. So for now, the next thing we can do before jumping into the specific states is actually creating the finite state machine itself, which will be a node because it will be attached to the battle unit. So let's go back to 2D view, right click on our components folder, create a new script, and we'll call this finite state machine.gd. Click on create and double click to open it up in the script editor. And again, please remember that we want to make this as generic as possible so we can reuse it if we want to, even across projects, right? So let's start by providing a custom class name called finite state machine. For debugging purposes only, we'll have an export variable for a label node, which we can use to display which state the state machine currently is in. This is optional, so for this component to work, we don't really need that debug setting, but I figured that this is quite useful when you want to test how a state machine works, so I decided to leave it in, even in the final version. We also have another variable called state, which will hold the current state the state machine is in. And we only need to create one method really here, which I called ChaseState, which takes in a new state as a parameter. And the first thing we do inside is we check if we are currently in a valid state or not. Because if we are, we need to exit that state first before going to the new one. Now, if we do have a valid new state, we can update the debug labels text, and we just grab the script name for the new state. So we basically have the class name displayed. But what's more important than the debug text is that we call the new state's enter method, right? And finally, after we enter the new state, we update that member variable and set the state equal to the new state. And that's it. A state machine is this simple. In that component's case, we don't really want to handle physics process and process here, right? Because we are not 100% sure that what this state machine will be attached to. We'll leave that to the UnitAI. This finite state machine only handles changing from one state to another and also displaying debug information on a label node. Optionally, what you can also do is you can provide a signal if you want to that the state machine has changed to a new state, but for this project it wasn't really even needed to do that, so I just left it out. It might be useful if you want to reuse it, I'm not sure, because your specific states can also emit signals, and I found that to be much more useful, as you'll see when we actually code the unit's AI. Okay, so let's save this with Ctrl S, and we're basically done with the reusable part, right? We do have a finite state machine in the state RefCounted class, which we can use as foundation for building state machines in the game, or in any game really. Now, if we go to 2D view and press Ctrl-Shift-O and search for battle unit, we can actually add the finite state machine as a new component to this. So let's go ahead and do that. Select the root node, the battle unit node, press Ctrl-A or click on the plus sign here and search for finite state machine. Click on create or press enter. Let's drag this up. So now we have a finite state machine attached, and you see that we have this debug label export variable, which we might want to use. So let's create a label for it as well. Select the battle unit node, the root node again, press Ctrl-A or click on the plus sign and search for label. Let's double click and rename this to something like finite state machine debug label. Let's drag it up to keep things organized. And let's test it with the text. So let's type in something like ChaseState. And what I would do is I will go to move mode by pressing W or clicking on this icon here. And let's drag it up a bit. And also we can make it a bit wider because we'll have AutoAttackState, which is probably the longest word here. Yeah, so let's, oops, not triple T. Let's make it something like this. And also we can center the text on the horizontal axis. And under layout and transform, we can set the size to, I don't know, maybe 130. And to center it, we can set it to -65 on the X. Yeah, I think that works. And for now, we can just delete the text because we'll set this from code. And now we can just make that connection between them. So if we select the finite state machine, click on assign and select the FSM debug label. So now whenever we change the actual state machine's current state, this label will be automatically updated so we can see it inside the game, which will be quite helpful for debugging. So let's go back to select mode by pressing Q and save the scene with Ctrl-S. If you like my content, please consider checking out my Ko-fi page where you can donate one time or become a member and get early access to all my content and videos. So for now, a lot of things are placeholder, and this is not the final state machine by any means for the battle unit, but this is a good starting point. So what we'll do is we'll initialize the AI, and enabling the AI starts with going into the chase state. So first of all, we'll try to chase an enemy. And when a frame ellipses, 3 things might happen. We can get stuck if we cannot move anywhere. Remember, in the unit navigation, we have this -1, vector, which represents that the unit cannot move anywhere. So when this happens, when we get back this -1 from the unit navigation system, we know that we are stuck. So we go into the stuck state where we wait for some time and then retry chasing again, because most of the time when we wait some time, one of the neighboring tiles will become available, right? And if we're not, technically we can get stuck again, right? Because we re-enter the chase state, a frame ellipses, and we're stuck still. The other thing that might happen is that we finally have a target in range, and in this case we can change to the auto attack state and start auto attacking the unit. This will be a placeholder. This flowchart does not end here because auto attacking has its own things, right? Here we can generate enough mana to go into the casting state, or it might happen that our target dies or goes out of range, and we need to handle all those events, but for now this will be just a placeholder print message that we should start auto attacking. And the third case is probably the most common one in this example, when we are neither stuck nor we have a target in range. In this case, then we just keep doing what we do. So we don't change any states, we just go back to this chase state and do the next frame in a similar fashion. So this is the structure we are looking for in this episode. In order to do this, we need to implement the UnitAI, but this will be the last thing because it's rather high level, right? We can only sort of conduct this whole thing, this flowchart, when we already know how our states work. So first we need to do these 3 specific states, and when we are done with those and we have the logic in place, then we can sort of do this whole high level thing, managing the transitions between them. So going back to Godot, we can start implementing our specific states. I think putting these in the components folder would be a bit awkward because they are not really reusable. These are all very specific to the battle unit logic. So we can collapse the components folder for now, and I think the same is true for the custom nodes. We call these custom nodes for specific things like the unit navigation system, the unit grid, all that stuff. And if you remember, states are not really nodes. They are RefCounted. So putting them here also doesn't really make any sense to me. So what I ended up doing in the reference project is I expanded scenes, went into the battle unit folder, and here I created a new folder inside called AI. And inside that AI folder, I dumped both all the specific states and the UnitAI component. Because again, the UnitAI is very specific to the battle unit. We cannot really reuse it anywhere else in the project. So that's what I ended up doing, but let me know in the comments if you have any better ideas. Okay, so let's right click on this and create a new script. Let's call this the ChaseState. Let's start with that one and inherit not from the node class, but from our own state class we just created. So click on create, expand the folder and double click on it to open it up in the script editor. This is probably the most complicated scripting we'll do in this episode. And mind you that also there's going to be a lot of placeholder stuff here, which we have to revisit later on. So the first thing we do is we introduce a custom class name called ChaseState, and then we'll provide two signals. So in this version of the finite state machine, we use signals to sort of signal out to the AI that a crucial thing happened inside this state. In this case, we have two signals which both trigger a change in the UnitAI. One is when we reach the target and we also pass the target as a parameter, and the other signal is when we are stuck in a position. The reason why I think this solution is pretty elegant is because the ChaseState itself is not really concerned with what happens when these things occur. It just sort of signals it out, right? Do whatever you want to do with the information. I think it's a clever use of signals. Also, we have three member variables, one for the actor unit, which in this case will be typecasted to a battle unit. Because remember, we have an actor in the state GD, right? Which is a node. And I know it's a bit superfluous or like having two separate variables, but to make sure that we get autocomplete, I just introduce a new member variable, in this case, which will be a battle unit. So we only have to do the type conversion once. We'll also have a variable for a tween because we'll use tweens to move the units between the tiles, and also a target, which will be a battle unit as well. The first thing we want to do is we want to override the enter method we have in the state class, which if you remember here, it's empty, right? So in this case, if we want to do something in a specific state, we have to redefine that method, which is exactly what we're doing here. So when we enter the ChaseState, we do two things. One is that type conversion I was talking about. So we reference the actor, which will be set when we create the state with the init, which we have inside the state, right? Remember that this method will be called when we create the new state with a new keyword. So we need to pass the node as a parameter. This is again useful to making sure that this is reusable for any kind of node. So what we do here in this specific case is that we define a new variable and do this typecasting once. And I think it's a great price to pay, so to speak. Like you might say that from a performance perspective, it's not really the best decision because we essentially have two variables storing the same information, which is absolutely right. But I don't think it causes that many problems when we only have like 20 battle unit stops, right? In an RTS game, this might be a considerable boost in memory usage, but as we always say, only optimize when you need to, right? And I think it's much better than typecasting the actor variable in all occurrences in the script. Because you see, the other thing we do is we set the target for a unit. And to reference that, we need to know what team the unit is in, because the player units will target an enemy unit and enemy units will target a player unit, right? So to access this, we call actorUnit.stats, which is the unit stats resource, and we reference the team enum. And since we do this type conversion, this will be auto-completed in the editor. So how do we set the target? For now, this is super simple and not at all what we'll use in the final game. But just to make sure it's not overwhelming in one episode, I decided to go for a temporary solution, which is in this case pretty simple. We'll grab a random unit from the opposing team, basically. So we'll see if the team the unit is on is the player team. If that's the case, we'll grab one randomly from the enemy units group. Otherwise, we get one randomly from the player units group. And whenever we enter the chase state, we pick a new random target. Of course, that's not really the best in this kind of game, but again, we'll replace this in the future. What else we want to do? We want to provide a public function called chase, which will be sort of the bread and butter of this whole chase state. So what does it look like when we chase? First of all, if we have a running tween, we can return from this method immediately because we want to tween from one tile to the next. And if we call this chase method again and again, when the unit is moving from one tile to the next, we don't really want to do anything, so we can return from this function immediately. Then the interesting bit begins. So we'll grab the new position we want to move towards from the unit navigation class, which we implemented in the last episode. So remember get next position. If we press and hold Control and click on it, expects two battle units. One is the moving unit and one is the target, and it calculates the path leading towards that unit. Now the actor unit will be the moving unit and the target will be the one we picked in the set target method. And since this is a member variable defined at the top, we can reach it in all of the methods. So now that we have the information where to go next, we need to handle the different cases. First of all, it might happen that we have nowhere to go, right? Meaning that we return this -1 vector from the unit navigation method. But this does not automatically mean that we have to go to the stuck state. Why? Well, because we have two cases here. If we have any targets in range, then we can end the chase prematurely, basically, or regardless where to go next, right? Because it might happen that a unit would be stuck, but still it has a valid target in range, and if that's the case, then we want to start attacking the target, right? But if we don't have any valid targets in range, then we can emit the stuck signal, saying that we are truly stuck in this position and we can neither move nor attack. These two methods are yet to be implemented, that's why we have these error messages here. And it doesn't really matter which one happened if we have nowhere to go, because this if is true. When we handled either ending the chase or emitting the stuck signal, we can return from this method because everything we do after only needs to be done when we can actually move to a new tile, right? So what do we do to move to a new tile? We'll create a new tween for the actor unit, call the animation player's play method, and bind move as a parameter. So what this does essentially, if we go back to 2D view for a sec, what this does is the same as selecting move in the animation player and starting to play, right? And since this is a looping animation, this will play on loop. So we do that here, and then we actually tween the global position property of the unit to the new position. And for how long is up to us, or really you, depending on how you want to implement your game. In this case, what I opted for is a constant variable, which we are yet to define. But it's not that trivial because I think these AutoBattler types of games can have a movement speed property or value for units. So just like you have attack damage and maximum health and mana, you might decide that movement speed is a variable you want to have inside your game. If that's the case, then you would probably, instead of using a constant like I do, you would probably want to reference the moving units, or in this case it's called the actor unit's stats, resources, movement speed property. I decided not to go for a movement speed skill or stat for units because it looks fine when they move with the same speed. But we do have to actually add this constant to the unit stats script because we don't have one yet. So we'll do this when we're finished with this script. And what happens when we finished the tweening? Meaning that the unit has arrived in its new position. First of all, we can kill the tween, and then again we have two different cases, right? So when we arrive at a new tile, two things might happen. We either have a valid target in range, which means that we can end our chase. It's basically the same that we have here with the -1/-1. If we moved one tile, it might happen that we weren't in range before, but now we are in auto attack range. And if that's the case, we can end the chase. But if we are not in range but finished moving one tile, then we call this chase method again. So this method can be recursive. What this means is that the method calls itself. So remember, we are still inside the chase method, right? So when we moved one tile, it might happen that we want to do the same logic and play the whole thing again. And this is where we do it. Let me pull up this flowchart again just to make sure that you understand. We are in the chase state, and basically the whole chase method is where this logic happens, right? We already handled being stuck, emitting the stuck signal, but when we are not stuck and not in range, this part, that's where we do this, right? Because when we are stuck, we have to check if we have a target in range or not, then go to the auto attack state. But we have to do the same when we actually move one tile. So it might happen that we have a target in range now, but if we don't, then we have to redo the whole thing and chase again. Hopefully it makes sense. Now all that's left to do is implementing those two missing methods. One is checking if we have a target in range, and one is for ending the chase. So ending the chase for now just means emitting the target reached signal and passing the target as a parameter. This might change in the future when we implement more stuff. That's why I did a separate method for it. And hasTarget in range is a Boolean method. It returns true or false, but it's really a placeholder for now. So we'll have this target finder or target selector component, which we will implement later down the line. And this will provide an elegant solution to picking these targets. But just like picking a random unit from the enemy group for now, we'll use this magic number. I experimented with it, so we'll just use 35 for now. And we say that if the target's global position minus the unit's global position, which is basically the distance between the two units, we'll grab the length of that vector and see if it's less than or equal to 35. We'll just say that it's in range. This is obviously really bad code. The reason why I did this is because we have a lot of systems that we are yet to implement to make this actually nice. Because units might be ranged or melee, right? So we need to handle their auto attack range, and we need to handle picking the right target and all that stuff. So just for avoiding this to be overwhelming or a 3-hour episode, I decided to split this into multiple parts, and for now we'll just use placeholder stuff like this. And now we are basically ready to go with the ChaseState. That's all the code we need. But we still have this error message here because we don't have that constant inside the UnitStats class. So let's save this with Ctrl S first. Now press and hold Ctrl and click on UnitStats. And let's add a new constant called move1TileSpeed. And for now, I'll just leave it at 1. Or if you want to use fractions here or floating point values, which makes sense, we can leave it at 1.0. And you can experiment with the different speeds. This is in seconds. So this is moving 32 pixels in a second, right? And we'll see if that's too fast or too slow or whatever value you like. Again, you might want to do this on a per unit basis. Then we would just need to add a new property for movement speed. And then you can set it on a per unit basis. Right. So if we go back to the ChaseState, this error message should disappear because now we do have that constant we referenced. And with no error messages left, I think we're done with the ChaseState. So the good news is that ChaseState was probably the most difficult thing we needed to code in this episode. Now we just need to do the other two, the StuckState and the AutoAttackState. So let's go back to 2D view, and inside our AI folder, right click on it and create a new script. Let's call this stuck_state, extend from the state class, click on create, and double click to open it up in the script editor. This is pretty straightforward. So we'll provide a custom class name called StuckState. Then we'll have a signal called timeout, and we'll emit this when we waited the amount of time we need to wait before retrying that chasing state. And we can provide a constant for the stuck wait time we want to use for the project. I just used half a second. And then we'll have a member variable for tracking the time elapsed after entering this state. And what we do is we override the physics process method. Again, no underscore here, because this overrides that custom physics process method we have here. So calling this won't be handled by the engine itself because these are not nodes. So remember, we need to do this on our own, and we'll implement this in the UnitAI component. So what we do when a physics process frame ellipses is we add the delta time to the elapsed time, and we'll check if the elapsed time is greater than or equal to the time we want to wait, and if it is, then we emit the timeout signal, so the AI can be notified that the stuck state expired, so to speak, and we need to handle it accordingly. And that's pretty much it. Really straightforward, I think. We can save this with Ctrl S and do the last one, the AutoAttackState, which will be just as easy, mostly because it's a placeholder for now. So let's right click on the AI folder again, create a new script, call this AutoAttackState.gd. Make sure it inherits from the state class, click on create, double click on it. And for now, what we'll do is really straightforward. We'll provide a custom class name called AutoAttackState. We'll have two member variables. One is the actor unit who's attacking, and one is the target. And we can actually override the init as well if we want to. And we'll do here. So when we create a new AutoAttackState, we will already pass in 2 arguments. One is the actor, which will be a node, and one will be the current target, which will be a battle unit. And we'll just assign those 2 member variables. And for now, what we do is when we enter auto-attacking, we'll just set the actor unit member variable as well to make sure that we cast it to a battle unit. So we have auto completion. And for now, we'll just print that this unit should perform attacks. And we'll print it once because we'll enter this auto attack state once and we won't go anywhere from this state. So basically when a unit reaches a target in this demo, then he will just stop and say that, okay, I should attack this other unit. Okay, so let's save this with Control S, pretty simple for now. And now all that's left to do is to do the UnitAI custom node, or whatever we want to call it, where we orchestrate all these state transitions. So that's what we'll do next. Let's go back to 2D view. And I just used the same AI folder. Technically, we could put this under custom nodes as well. I don't know, maybe I'm not that consistent with my project organization, but I felt like it belongs more in this folder than it does in the custom nodes. So let's create a new script here, if you agree, call this UnitAI, and this will inherit from the node class. Because remember, we do need to have access to the physics process callback, and the process callback, so we can call it on the states themselves. Okay, so how do we code this flowchart, these transitions? First of all, we'll provide a custom class name and we'll call this UnitAI. And we'll have 3 export variables. One will be a boolean to enable or disable the UnitAI. And this will have a custom setter function, which we'll implement in a second. And we'll also have an export variable for the actor, which in this case will be the battle unit itself, just to make sure that we can pass this battle unit when we instantiate new states. And we'll also have an export variable reference to the finite state machine, which you can see is completely independent of the unit's AI, right? So that's the reason why we have 2 different scripts, because then if we'll have anything else that needs a finite state machine in the project or even in a different project, then we can just copy that component over and we don't really have to worry about deleting the stuff that we don't need. So what do we do when we change this boolean called enabled? Well, first of all, we set the value, and then when we enable it, we can start chasing a target. But if we set it to false from true, then we make sure that the finite state machine's state will be deleted. So we change to a null state, which is a non-existent state. When we toggle this enabled property, we cannot really cause bugs with being stuck in an auto attack state, for example, right? So we just make sure that when we disable this, then we change to a null state in the state machine. And now we can override the underscore physics process method because this is a node derived class, right? So it sits inside the scene tree, so we do have access to the physics process callback. And what we do is we have this safeguard to make sure that if the UnitAI itself is disabled, then we can return from this function immediately because we don't really want to execute anything in that case. But if it is enabled, then we grab the finite state machine's current state and call its physics process method without the underscore, right? So if I press and hold Control on this, you'll see that it's an empty method by default for all the states, but for the StuckState, we actually have this logic, right? So the UnitAI itself will be responsible for executing that state's physics process in every physics tick, right? We'll virtually do the same for the process method, just call process instead of physics process. Again, no underscores here, but we do have the underscore for the node itself. And we need to implement that start chasing method when we enable the AI component. So what do we do? How do we use these specific classes? Well, since we have a class name provided, what we can do is we can create a new variable called ChaseState, and we can use ChaseState.new to create a new instance of that RefCounted class. You'll see we have to pass in the actor as a parameter because if you remember, the ChaseState is a state, right? And if you take a look at state.gd, all state-derived classes have this init method where you can pass in an actor as a node to set this member variable. That's what happens here. That's why we have this actor in the parentheses. And when we have the ChaseState to implement that flowchart logic, we can already establish connections, right? So we say that when the ChaseState emits the stuck signal, we'll provide a callback method called onChaseState stuck, And we make sure to signal that this is a one-shot connection, meaning that we can only execute this callback method once when we emit the stuck signal. So if for whatever reason we would emit this signal multiple times, we won't execute the logic multiple times as well. We just want to do this once. And we do the same for when the target is reached, when we are within attacking distance. We'll just call a different callback method, right? And after we establish the connections, we can call the finite state machine's change state method. We officially change into the chase state. And I left the blank line on purpose because after we did that, and just after, we can call the chase state's chase method. If we press and hold Control, remember this is the one where the bulk of the logic happens. Why do you think we need to call this after? What's the reason to put this here? Well, it's because when we change to a new state, what we do in the finite state machine is before actually setting the variable, we call the enter method for that state. So in terms of the chase state, what this means is before calling this, we want to call this. And this is crucial, right? Because we want to set the target we want to chase before we actually start the chasing process. So the order of execution really matters here. Because when we call this line, we'll call the enter method of the chase state, set the target, and then we can start chasing our target as well. So far, so good. The next thing we want to implement are those two callback methods. So what do we want to do when we emit the stuck signal from the chase state? Pretty straightforward. We want to act according to the diagram, right? Or the flowchart. We'll create a new stuck state, pretty similar to what we did with the chase state. And this time what we do is we connect the timeout signal of that stuck state, when we waited half a second, to the already existing start chasing method, right? And again, we only connect to it once. So whenever this stuck state expires, we'll retry chasing a target. And then after establishing the connection, we also want to change to that new stuck state, making sure that we actually enter that stuck state and that this will be the one that gets executed on every physics stick, right? Because we use FSM.state here. And we'll change to the new state when we call this method, right? So if we leave out this, then we never actually enter the stuck state or start counting half a second because we will be still in the chase state. And for the chase state, nothing happens in the physics process tick. So what we want to do is to make sure that the finite state machine's current state will be the stuck state, so we change to it. Finally, we want to handle reaching a target, right? So reaching this actually has a parameter. This signal actually has a parameter as well, which is a new target. So in this case, pretty straightforward what we want to do. Create a new AutoAttackState with the two needed values, the actor and the target, and call the finite state machine's change state method to change to this new AutoAttackState. And that's it. Hopefully you can see how this high level logic or how this flowchart can be implemented inside the engine with this solution. Now we have all these transitions between the finite state machines. Some of this are handled by the states themselves. Like in this case, waiting some time is handled by the stuck state, but mostly these transitions are tied to signal emissions, like the timeout signal from the stuck state or the stuck or the target reached signals from the chase state. And that's all the coding we needed to do for this episode. We can save this with Control S. And let's not forget that we actually need a UnitAI added to the battle units. So let's go back to 2D view. Select the root node, the battle unit node, click on the plus sign or press Ctrl A and search for UnitAI. Let's drag it up and we need to assign the actor and the finite state machine. So the actor will be the battle unit and the finite state machine will be the finite state machine node. And now that we've set the export variables, we can save the unit with Ctrl S. Phew, okay, that was a lot of coding. And the really final thing we need to do is to hook this up inside the arena for the battle handler, right? We need to initialize this and somehow test if enabling the UnitAI works or not. Okay, so to test this, what we need is going back to the battle unit for a second and open up the script for it. And in order to enable or disable this from the battle handler, we need to have a reference to this because we only reference these components or nodes so far. So let's press and hold left mouse button and drag this over and release by pressing Control. And just to make sure that the order of these components match the order in the scene tree to keep things organized, I'll press and hold Alt and press the up arrow to move this above the animation player. Save this with Ctrl S. And now if we go back to the arena and click on the script for the battle handler, we need to provide some sort of testing code for the AI. So let's scroll down, and between the ready and the setup battle unit, we'll again inject some test code here. And what we'll do is we'll say that when we press the test 1 button, which is Q for me, we'll grab the first player unit with the get nodes in group call, convert it to a battle unit so we have auto completion, and we say that the UnitAI components enabled property should be true. And when we set it to true, that unit should start chasing a random enemy unit. So that should do it. Let's save this with Ctrl S and play the game finally to see what we created. Okay, so if we buy some units and start a battle, if I press Q, you'll see that we have this chase state above Robin's head. And you can see, since we have the path debug as well, this is the unit we targeted. And we go to the auto attack state, and the unit essentially gets stuck in this auto attacking state. And we should have a print message that this battle unit should perform attacks. Awesome. So it kind of works, but it would be also nice to test the stuck position as well. So what we can do is we can copy this code, and for test 2, we can grab the first one from the battle units. So we can manually enable the AI on 2 of those units. So now if I press Q, Robin will start moving. If I press E, Björn will start moving. So if I start with E, then Björn should be in the stuck state with no move animation playing, and also re-evaluating if he can move after half a second ellipses. So if I press E, you'll see that Björn is in the stuck state, and no matter how long I wait, nothing really changes because he still cannot move. But if I press Q to start moving Robin, you'll see that Björn sort of frees himself and finds a valid position to move to. So now both chase states will be executed and they move on to their auto-attacking form. Pretty awesome. So these are the foundations for our UnitAI system and a reusable version of a finite state machine with the RefCounted class. But one final thing we can do is we can get rid of this testing code if we are sure that it works. And now we can save with Ctrl S. And that does it for this episode, and I guess I'll see you in the next one. Bye bye.